Hi everybody, I'm Sarah, like she said, and this is Everybody Talks. Sick. If you don't know who I am after I literally just said it, don't worry about it. Cool. So this talk is only 35 minutes, and there's a lot of information. So here's the thing. I'm gonna set goals. My goal is that my Fitbit doesn't think I'm doing cardio. Your goal is to learn one thing. Also, I'm gonna speak really fast because there's like 97 slides. So, back in the good old days, and by good old days, I mean like a year ago for me, I was a consultant, I was a systems engineer consultant, and I'd go to these large enterprises, and they'd be like, hey, we have a problem. All of our IP addresses are hard-coded, and so when one of our servers in these back rooms go down, like, it's a big deal. I was like, I don't think you should be doing that. So I kept having these problems where, like, basically there was like 30 Drupal sites on one of these servers, and when they went down, it was a whole big deal. And I'm pretty sure Armon had this exact problem probably longer than a year ago. And he actually did something about it. I just complained. So what did he do? For reference, this is Armon and Mitchell. They're our co-founders and CTOs. If you don't know who they are, I can't help you. So to try and fix this hard-coded IP address problem, we first had to figure out how a model in which we wanted to share information in the first place. So we were trying to find the most fault-tolerant, scalable, and simple, hippest thing. At the time when we were looking for this kind of solution, we were just hoping it would scale up to 5,000 nodes. This led us to peer-to-peer, fully decentralized communication. So this is a lot of words that I hear in meetings with the console team, and I'm like, yeah, I know what that is, and I don't. So I'm gonna explain it to you, so if anyone says it in a meeting for you, you're like, I actually know what that means. So a hot topic since like the 1960s has been decentralization. If you don't know this, fun tidbit, when the internet was first starting to be founded, they wanted it to be decentralized so it would be more fault tolerant. Things like the army and the military were supposed to use it, so it needed to withstand disasters. So decentralized basically means we don't rely on one source of truth for the data. Here's a pretty picture of it. So basically centralized means we're all going to that one source of truth for that information. Decentralized means we have many different sources. So peer-to-peer. Admittedly, sometimes I play Destiny 2, and I play it very badly. But when someone says peer-to-peer, I always think of gaming. So a good way, so this is a good image too, but a good way to explain peer-to-peer is basically when you're a gaming company like Destiny 2, you might want something super cheap to run all of your matches, right? So instead of having your own dedicated servers, you can offload that onto the people who paid for the game. So what happens is when I join an online match, then someone in the match is chosen as the host, kind of the center of truth for the data. The rest of us become clients, kind of huddled around that person, hoping that they have good internet. In the case of P2P, there are no dedicated Bungie servers behind the scenes checking like every shot, kill, death. It's just another player, or it could be me. In the case of like something like Counter-Strike, they have dedicated servers checking every movement you do is valid because they're like serious gamers or something. So from here on out, it's just best to kind of believe me when I say peer-to-peer is decentralized implicitly. So now that we know what this means, what do we do with this? We still have that IP address problem. So after evaluating a lot of protocols and Armon reading a lot of white papers and doing some math stuff, he was like, gossip protocols are dope. So he did some research on different gossip protocols, and he was like, all right, how do these work? And which one do I like best? If you've seen my RAF talk, you'll know that there's different kind of protocols and ways to implement solutions to these problems. So you can have many different flavors of gossip. So gossip protocols, how do they work? A really good example of this, if you haven't been to high school for some reason, is one my boyfriend gave me. He was in the Air Force, and he told me that whenever you broke a glass in the mess hall, that person would have to announce, broken glass, be careful. Everyone who heard that would then have to relay that. So one person break a glass, he'd say broken glass, be careful. That person who heard him would have to say that, and so forth. Every time you hear it, you say it, right? If you're in high school, like I was, you'll know that when Jenna woke up and decided to make a rumor about you that morning, and she told her friends, then by 5th period, everyone knew. Gossip spreads, and you can see it through these real-world examples, how simple but effective it is. So there's a couple different types of gossip protocols, and I'm gonna try and keep this light for you. But there's structured and unstructured. Structured being like rings, spanning trees, stuff like that. They're complex, but the trade-off is they're more efficient. But if the structure is broken, it makes things kind of hard to fix. Unstructured, being things like epidemic broadcasts, are simpler and more fault-resistant, but they're slower. Another important consideration we took was limited visibility versus full visibility. Basically, this means like if you have like 3 little rings of people and they only know their little neighbors, and they're just kind of like in control of who's next to them, they only know a few of the members in the cluster, versus the whole cluster knowing everyone in the cluster at all time. So our trade-off here again is full visibility is of course simpler to understand. It's less complex, but it's harder to keep that information up to date because there's so much of it, versus increasing complexity, but it's faster. You'll see this kind of trade-off situation happens a lot. And then finally, what we chose was gossip, something peer-to-peer, something unstructured, something full visibility, and something simple, because we do believe in like keep it simple. So that brought us to SWIM, our flavor of gossip we decided upon. We're going to talk through SWIM's acronyms and some of the features that make up SWIM. Cool, scalable. I really hope some of you guys know what this means, but SWIM is pretty scalable. Like I said, originally we wanted it for 5,000 nodes. The scalability extends into how it was built around sending probes and not using heartbeats, and I'll cover more about heartbeats in a little bit. Weakly consistent. If there's one thing I learned about consistency when I was researching this talk, because I thought consistency was cool, is how inconsistent information around consistency is. That's my favorite joke. And anyways, so weakly consistent means basically it might take some time for an update to eventually get consistent throughout the cluster. Basically, it takes like 10 seconds or a minute for everyone to have the same information. And data loss could occur if a node fails. Say you send an update, but before that node can tell someone else, it dies, well, you're gonna lose that information. It typically, this typically will converge in about 2 seconds, but it's not immediate, and this can have problems with people. One of our UI guys on console was basically complaining about weakly consistent stuff. I never thought it was a big ideal or a big problem because I never work on things that I need the information immediately, but he did. So I realized weakly consistent cannot be good. But this paper touches on why they did this. Basically, less strong consistency model, not as difficult to understand. So the TLDR is literally that, what I just said. I'm a slide ahead of myself. All right, an infection style process group, basically a snazzy way to say epidemic or gossip style broadcast. And membership, SWIM seeks to answer the question, who are my members? Right, so now we kind of understand what SWIM is, what the acronym means. Some key properties of SWIM is in its scalability and failure detection. In SWIM, no matter how large the group size is, the load per member will stay the same just because we are sending messages out at the same rate. This is what that graph shows. For failure detection and latency, this is also independent of the entire size of the cluster, We'll cover this more in the failure detection section, but our rate of announcing failure when we have a failure, it always stays the same. So we use Gossip to send out membership updates across the cluster. Man, I'm at cardio mode. Okay, so what does swim give us? Like, if I was having to give this talk in 15 minutes versus 35, what would I show you? Well, it'll give you the membership updates, joining, failing, leaving, just these 3 basic things. Failure detection, and it focuses on disseminating information of the failure detection and of keeping the joins and leavings up to date. So basically, fun fact in the swim white paper, this might be interesting, is swim focuses on having 2 lists of members, one that is up to date and then one is for the failure ones. So, and then it will converge on that information and have a complete up to date list of members. All right, failure detection. This one's fun because we have pretty images. All right, so we're gonna break down Gossip a little bit more. So in here, node G is like, hey, node B, what's up? Are you alive? Let's be chill. And then node B's like, yeah, I would love to be chill with you. And then we all talk about how chill node B is. But let's say you and node C got in a fight last week, and node C is not talking to you anymore. So you're like, hey, are we cool? And node C doesn't respond. All right, whatever, node C. I'm gonna ask node A and a couple of the nodes to be like, hey, I can't reach B right now. Can you see if they'll talk to me? And guess what? Node C won't talk to literally anyone. This is a huge deal. And so you know what? We all won't talk to node B anymore. We're gonna say they left our friend group. So there you go, that's your failure detection. If I can't talk to someone and my friend can't talk to someone, then I'm not gonna be friends with them anymore. They're out of my cluster. And you can think of Gossip as just like high school, because there you go. It's the worst way I've done that one so far. All right, incarnation numbers. This is cool. So basically, if I send out a failed message, but that node is actually alive, how do we make sure, who's most up to date? Who is the, who has the most recent time, basically? If we're not gonna use a local clock, what do we do? So an incarnation number basically starts at 0, and every time we receive information about a suspected failure, we up that number. It's only hosted in the local node. And so basically, whenever we receive a suspicion about ourselves, but we are not failed, we up that number. And we say, hey, we're alive. Okay, so swim is like our recipe. We take sugar, spice, and some robust failure detection, and member list is made. All right, so you probably never heard of this, but you can go to github.com/happycorp/memberlist and you can see it. So basically what happened is Armand was like, yo, this paper's dope, but I need to make code around it. So he and other people made member list. And in our case, member list is like Buttercup, strong, reliable, and for some reason grumpy. So the basics for member list. We have our 3 that we had from swim, alive, suspect, and dead. We have indirect and direct probes, and our member updates piggyback off of those probes. Okay, so we added a bunch of additions on the member list, and I'll try to cover them pretty quickly. But since member list is our version of swim, there's some cool enhancements. We added TCP and UDP for probes. In typical swim, we would only use UDP for probes. We sometimes send direct probes via TCP in case there may be an issue with traffic being routed incorrectly or our network is misconfigured. If basically you don't have UDP configured, then guess what? We're not gonna be able to talk, so we use TCP instead. We also added some anti-entropy mechanisms that allow random members to sync at random intervals so that all of our state can kind of converge at a quicker pace. And lastly, a problem we were having was membership updates not being sent out frequently enough. In the swim paper, it recommends making the interval at which probes happen smaller, so the probes would be more frequent. However, what we did was we set out a separate layer that we can send out memberships updates in. Also, we did a bunch of research and even have our own white paper. I think it's called a white paper, but it's a paper, and it covers some of the improvements we added to swim and why. And I'm gonna touch on them really quick. So, we added some self-awareness. So basically, if I ask for a liveness check and I don't receive a response in time, maybe I was too slow to process it. Or if I suddenly receive a large number of liveness pings, maybe the cluster thinks I'm offline, and I probably shouldn't suspect other members if I'm appearing offline. So basically, this is me kind of reflecting on myself and everything that's coming towards me, and then being able to like change my intervals and probes based off of that. Next up, we have a dog pile. This is a quote from my actual dog. And so, dog pile, he's smart. For each node there's a suspicion timeout before we decide, yeah, you're dead. For new suspicions, ones we haven't ever heard before, we let the timeout last the longest. We'll believe, since this is the first time we've heard this suspicion, that it's not true. But over time, we might receive more suspicions about a particular node. And the more we hear that another node is dead, the more we start to believe it and lower that timeout. So Dogpile assists with message processing and removing failed nodes, even in times of high resource utilization. And then Buddy System. Buddy System basically prioritizes sending suspect messages so that if a node's actually alive, it can refute it quickly before the suspicion timeout ends. If you really like this, John Curry in our research department, he did a talk about it because he did all of this. Cool. Fun fact about this. At HashiConf EU, I was sitting with Paul Hinsey at a table, and I was like, what's a keyring? And he was like, just imagine you have like a keyring. I mean keyring for computer, not keyring, but it'll tie in. So imagine you have a real life keyring with a lot of keys on it, and you smash it into a door, and then eventually one gets in and it opens, and that's a keyring on your computer. Very good definition. So this is for him, but memberless uses a keyring that can encrypt all communication as well as decrypt communication. Memberless will first use the first key to encrypt any communication, but will also store old keys to decrypt any communication in case we get any encrypted message we can't understand. All right, so we have member lists, and HashiCorp was like, well, we gotta make this good money. So, actual words in our meeting. And so we did this, and we made this. No one's probably heard of Surf. That's totally chill. But Surf was born, and Surf is smart and strong. So what is Surf? Oh, no, we're at the Surf part, just so you know where we're at. And I think that means we're halfway done. We need to go fast. All right. So what's the difference between memberless and Surf? Surf has new functions, Vivaldi, which we'll cover, clocks, and CLI. Memberless was just our base implementation of Swim. Cool. So what are our many functions? We have graceful leave, snapshotting, which just means we can snapshot and save the state. Network coordinates, which is fun and we'll talk about. Key manager, and Lamport clocks. It's coming up. So custom event propagation, if you actually want to hear more about this, you should come to my 12:55 talk. But custom events basically give you the ability to call an API and run a script or whatever to a member update. So basically say, if I get a message and the message is for me, then I will execute this bash script. Or if a new node joins the cluster, then I will run this Python script, etc. Vivaldi. So what Vivaldi does is it makes a map of network coordinates by calculating round trip times and doing a bunch of fun math things so that you can kind of see, it's like a 3D matrix. I don't know if it actually plots to a map, but it'll kind of group nodes in a cluster. So you could see where data center 1 and data center 2 and data center 3 are. Here's a video of it. Oh, please work. All right, so here's a great visual. This is how it kind of shows. You see how they all group up? That's kind of what Vivaldi does. And it might be good for assisting in failovers, maybe. If you want to know more about Vivaldi, Armand gives a talk about it. Check it out. That's how I learned about it. Leslie Lamport, my guys. All right, Leslie Lamport's back at it, and he decided, you know what I'm gonna do? I'll make Lamport clocks, because I don't like time. So, real life quote. So, Lamport clocks are event-based, which means for every event that happens on a node, we increase our Lamport time. There's a lot of complexity to this, and you can read his white paper if you so choose, but it keeps track of the time of an event occurred in a cluster so that we can refute events that we don't like anymore or that have happened in the past. We added a CLI in Surf. Very cool. All right, so what happened? Why does no one in this room except you guys now know about Surf? Well, people struggled to reason about the consistency model, and they wanted a central UI and API, so how do we give the people what they want? Raft. And one person. And if you go to our Raft library, you can contribute and I'll actually respond because it's my baby right now. So if you don't know about Raft, let me tell you about it. Say you have 5 children and they're all like, yo, we're hungry, because that's how kids talk. How do you decide on what all 5 of them want and not have to go to 5 different restaurants? In Raft, this is a simple way to show you the problem it solves, and here's how it does it. So, in Raft, we started up this 5-node cluster in Raft, and we have to decide on a leader. Each node will have a random timeout, and once the first one with the shortest timeout ends, it will say, hey, please elect me. And then if everyone can reach that node, they'll basically send a yes, we approve of you. I will elect you for the president. All right? The elected leader will then send out health checks before the other nodes reach their heartbeat timeout, just to say, hey, I'm still your friend, let's keep talking. In Raft, like Paxos, and that's notes from my last talk, but don't worry about Paxos. In Raft, we have 3 different states: follower, candidate, and leader. Raft is divided into terms because there is only 1 leader per term. Some terms have no leaders because there was a conflict or we just didn't decide. You can be a leader only if you have an up-to-date log. Raft is built around keeping the log up to date and being a source of information. So for leader election, you have 3 different outcomes that can happen. You're a follower, and you hit the end of your randomized timeout without hearing from the leader. You get worried, so you'll decide you'll be the leader. After requesting others' votes for you, you'll either become the leader, somebody else will become the leader, or nobody will. And then if no one does, we restart the leader election. For the safety of the log, one of the primary times the leader will be rejected if the candidate's log is out of date. We can do this by basically checking the log term and the log information against each other. Now say if you're a node, we're gonna skip this slide, go to the other one with pictures. Cool. Say if you're a node and your committed entries don't match up to the other the leader's committed entries, then the leader will start syncing logs with you to try and get that conflict resolved. If you care more about this, go see my talk that I gave last year. It's on the internet. Cool. I know I just really ran through Surf, but we only have 10 minutes. So Surf, or we ran through Raft. So Surf plus Raft is love. We're done. Console doesn't exist. We just threw Raft on Surf and it's all chill, right? No, because it's HashiCorp. And we were like, we're gonna make a new product out of this because some people actually use Surf, 1 person at least. So we made Console its own dealio so people could still use Surf, and I guess you can use memberlist if you want. So Console was born. And Console is Buttercup? I'm looking at Bubbles. Dang it, see I messed up. Console is Bubbles, and if you want to know, there was a huge debate about this, about who was who. Where are we at? We're almost at the end, my guys. We have 10 minutes. Maybe I went too fast. All right, so comparing the two, Basically, console added a lot of features that just piggybacked all the really crufty stuff we added in Surf. So, console basics. I'm sure you've heard a lot about console this week, month, whatever. So what do we have? We're strongly consistent thanks to Raft. We've implemented 2 gossip pools, WAN and LAN, and we do that with the help of Surf to keep consistency no matter where the member lists are, or no matter where the members are. And while for Surf has the focus at the node level, Consoles is more focused on particular services. Okay. This is like a huge deal. You know why? Because no one ever gets this right. I worked here for 6 months, and I still didn't know the difference between these words. And they're different words, and our community team will tell you that they still don't know what it is. So let's cover them, and then you'll know more than I do. So basically, in console, we have an agent. An agent is the process that runs the console, runs on every machine, and it can either be a server or a client. A server, which is a standalone machine, hopefully, practices in a lot of stateful activities within console. This includes participating in Raft and communicating across data centers. Lastly, there's a client. It runs alongside an application and monitors the application for us, as well as helps us to identify where the application is and when we want to talk to it. It is not stateful, by the way, and it cannot cross data centers, so it's specific to one data center. Yes, and under 100 now, just in case you were really curious. So, some cool things that are in console. So we have a key value store. You probably don't hear about it a lot, or maybe I'm just like new and like people don't like to talk about old things, but I think it's cool. So console's KV store is great for storing options for a config or keeping feature flags. It's strongly consistent because of Raft, and it's implemented in our own InMemDB that's based off of radix trees. This in-memory database is stored only on console servers due to them being stateful. However, both servers and agents can access it. All right, I told you we would talk about Vivaldi again, and he's back. So in console, we can use prepared queries. And here, we can use prepared queries basically to set over a failover that basically says like, hey, if I fail, find someone nearest to me and go talk to him instead. I think that's really cool, by the way. If you've ever had, I don't know, I used to work at a WordPress hosting place, and like, I think that's cool if someone's site goes down and you're like, don't worry, my site's literally next door, instead of like going to Canada or something. Just saying. All right, so service level health checks, since console is all about that service life, we can set around health checks that are pretty configurable and allows tons of different types. You can even use the Docker for it. So that's cool. Okay. So I started off this talk. I love the wow. I started off this talk talking about the IP address problem. It was in a client site, hard-coded IP addresses everywhere. Armand was pulling his hair out like 6 years ago trying to figure it out. You know, how does this help our initial problem? Well, console helps us by acting as our man in the middle here. Where in this example Nginx file, we use a proxy pass to forward request to another web server, and in this case, Apache. In the top block, we see this hard-coded IP address, right? But in the bottom block, with console configured properly, we can just call out to console, and it will handle the resolution for us. This is my favorite next slide. So console today. Talk to that guy. He's right there. Okay. 5 minutes left, and we're on the summary. Cool. Let's summarize. So we've covered a lot of information, from Raft to Surf to Swim to gossip protocols. I hope that you have learned at least one thing. But basically, a good way to talk about this is console cannot operate if the central servers cannot form a quorum. while surf will continue to function under almost all circumstances. This is because console, well, you want that centralized API UI. You want that strong consistency, right? But surf doesn't care. Surf can be decentralized, and all it worries about is keeping that member list up to date. And then member list, I don't know, that's your own flavor of life. But member list is fun, and you should check it out too. Cool. What next? These slides are really dope. You should, if you ever want slides like this, you should contact Lookmy. She made them. And lastly, I know this went really fast, and my heart rate went to cardio mode, so I was probably like breathing pretty hard. So I wanted to say thanks for sitting here for 31 minutes and listening to this. If you have any questions, comments, feedback, you want to tell me how cool I am, go ahead and hit up this tiny URL. It's a little Google form. You fill it out, and I read it, and I'll be happy about it. Thanks so much.